The Apollo program is heavily associated with a single event, Neil Armstrong descending a ladder to the lunar surface. Reaching the moon actually required a grueling, methodical campaign. NASA designed each mission to isolate and test a specific incremental capability. The very first crewed mission, Apollo 1, never launched. During a routine ground test in January 1967, a fire swept through the sealed command module, taking the lives of astronauts Gus Grissom, Ed White, and Roger Chaffee. The disaster forced engineers to strip the spacecraft down. They overhauled the hatch design, removed flammable materials from the cabin, and rewrote the program's safety protocols. The lessons from that fire created the foundation for everything that followed. Every crew that eventually flew to the moon relied on the hardware redesigns forced by Apollo 1. 21 months later, Apollo 7 launched. The crew stayed in Earth orbit to prove the overhauled command and service modules could function safely. Over 11 days, they verified the life support systems, navigation computers, and engines required to sustain humans in a vacuum. With the base spacecraft proven, Apollo 8 bypassed further testing near Earth. The crew fired their engines and navigated across 250,000 miles of deep space. They became the first humans to enter lunar orbit. Looking back at their origin point, they captured the Earth rising over the lunar horizon, revealing the true scale of the journey. Arriving at the destination was a massive technical hurdle. Actually touching the surface required the invention of a completely new machine. To reach the lunar surface, engineers built the Lunar Module, a fragile spacecraft operating entirely outside Earth's atmosphere. Apollo 9 tested it in Earth orbit. The crew detached from the main module, flew independently, and successfully aligned for redocking. Just 2 months later, Apollo 10 took the fully tested spacecraft stack to lunar orbit for a final dry run. The crew descended to within 9 miles of the cratered surface, calibrating their navigation radar and verifying the flight path, intentionally stopping their descent just short of touchdown. By testing the module in orbit and then simulating the descent at the moon itself, NASA broke an overwhelmingly complex landing into a calculated, executable procedure. In July 1969, Apollo 11 combined every tested step into a single mission. Neil Armstrong and Buzz Aldrin piloted the Lunar Module down to the Sea of Tranquility, securing the primary goal of the entire Apollo program. Landing safely in a wide, flat plain was sufficient for a first attempt. Future scientific expeditions, however, required touching down in specific, hazardous geological zones. Apollo 12 proved the navigation hardware could handle precision targeting. The crew landed so accurately they walked directly over to the Surveyor 3 probe, which had sat in the ocean of storms for 2 years. With this pinpoint landing verified, the moon transitioned from being a single, simple destination into a massive, highly varied, and fully searchable terrain. The danger of deep space re-emerged during Apollo 13. 200,000 miles from Earth, an oxygen tank ruptured inside the service module. NASA canceled the lunar touchdown immediately. The crew sealed themselves inside the Lunar Module, repurposing a craft designed for 2 days on the moon into a lifeboat for 3 men. Mission Control systematically worked through catastrophic power and water shortages, calculating complex trajectory burns to guide the freezing crew to a safe ocean recovery. Following months of rigorous investigation, Apollo 14 successfully navigated to the rugged Fran Bowo Highlands, the exact target originally intended for Apollo 13. The recovery of Apollo 13 and the successful touchdown of Apollo 14 demonstrated the true durability of the spacecraft and the teams managing them. With the transportation architecture fully verified, the final 3 missions dedicated their payloads entirely to advanced geological fieldwork. Apollo 15 deployed the Lunar Roving Vehicle, extending the astronauts' exploration radius by miles and allowing them to carry heavy geological samples. Apollo 16 used this expanded mobility to study the Descartes region, gathering data from the ancient, heavily cratered highland terrain. The scientific campaign peaked with Apollo 17, when NASA sent professional geologist Harrison Schmitt directly to the Taurus-Littrow Valley to study the lunar crust firsthand. The Apollo program was a methodical, highly engineered chain of steps. Through a decade of testing, failure, and adaptation, NASA turned a distant light in the sky into a comprehensible, explored world.